trailblazers in research, innovators in technology, and those who simply have a good story. All make up the fabric that is George Mason University. We're taking on the grand challenges that face our students, graduates, and higher education is our mission and our passion. Hosted by Mason President Gregory Washington, this is the Access to Excellence podcast.
Since putting the first man on the moon in 1969, scientists have continued to push our knowledge and understanding of life and existence in vast unknown frontiers of space. Whether through Mars colonies or alien life forms, we're all wondering what and who can survive beyond Earth's atmospheres. Joining me today is someone who's working to unravel the mysteries of life beyond Earth, both human and otherwise. Anamaria Berea is an associate professor of computational and data sciences, researching the emergence of communications and fundamental patterns of communication in both living and non-living systems. Anamaria has worked with NASA and others to help humanity boldly go where no man or woman has gone before. Anamaria, welcome to the show.
Thank you. It's good to be here.
Well, look, this is going to be really fun. You've got a lot of cool stuff you're working on, and I am really, really excited to jump into it. So let's start with your work at NASA. You were selected to participate in an independent study on UAPs, or Unidentified Anomalous Phenomenon. Our listeners are probably more familiar with the term that I grew up with, which is UFOs, Unidentified Flying Objects. So can you explain the difference between these terms, and what is the rationale behind the change in terminology?
Sure. So UFOs comes from unidentified flying objects, which was the original term that the community and the public used for several decades after the 40s, when we had allegedly the first observation of what more popular was called the flying saucer, right? But to get things more serious and into the scientific realm, scientists decided to change the name into unidentified anomalous phenomena, which is not necessarily about flying phenomena, right? So these can be any type of unidentified phenomena, maybe coming from the sea or subsea. Most of them might have been observed in our atmosphere. So the rationale for the change in the name has been to basically cast this serious scientific lens to the phenomena so that we can actually study it.
Well, that's interesting, because I'm going to tell you, you hear the term UAPs, and that sounds as mysterious and intriguing as UFOs. I was always afraid of them growing up because there was this connection with UFOs and UAPs in popular culture with extraterrestrials and alien life forms, right? But they're terrestrial objects, as you just highlighted, that could be included in the category of UAPs. Is that right?
That is correct. So the idea here is to actually emphasize the word unidentified, and the other word is phenomenon, right?
Right.
So I'm a scientist at the core. So for us in science, whenever we see something that we cannot explain or understand, we want to cast the scientific method and to try to understand this phenomenon. So it's science that draws that unidentified to identified, right? So what we have in the middle, whether it's anomalous, whether it's flying, whether it's terrestrial, whether it's under the sea, that is a different story. So that pegs to where that observation has been made.
Understood. So if we were to just pull back for a second and ask some very general questions about UAPs, like, what are the potential impacts of UAPs on issues of national security, right? Or on our economic structure?
So that is the big question, right? And when it comes to UAPs, we, for a very long time, we have not had actually scientists looking at this phenomenon. They did come mostly from the defense side, if I can say so. And one of the reasons they are still unidentified is due to all the classified observations. And these classified observations are not necessarily because the government doesn't want us to know what they are, but because they have been made by censors or people that were at the time under classified conditions, right? So obviously these can pose problems for national defense. They can pose problems on the economic side. They can also pose problems in the social realm. So maybe some of these Hollywood movies kind of allude to the idea that once the discovery of alien life is made, that we can potentially have riots, we can potentially have conflicts, which all of these will pose problems both to the national defense and to economics. But while popularly we are thinking about UAPs and UFOs connected to alien life, right, and whether we have alien life that is right here next to us, right, on Earth, that is not always a connection, right? So again, I want to stress the fact that we have an unidentified phenomenon that we don't know what it is. So it might as well be a new physical or atmospheric phenomenon that we haven't discovered yet, right? Because we don't know everything in science right now, or in physics or in chemistry. Maybe it is an optical phenomenon, right? So until we can actually scientifically analyze these, it's really difficult for us to say what are these things, right? And we cannot say that only based on public opinion, and we cannot say that only based on intuition or allegations. We do need rigorous scientific studies for this so that we can turn that unidentified into identified.
Understood. So you are also affiliated with the SETI, or SETI Institute, commonly known as the Search for Extraterrestrial Intelligence. Can you tell us a little bit more about that institute and a little bit more about your work?
Yeah, sure. So I've been affiliated with the SETI Institute for a few years now. Since before I was in the independent study panel with NASA, because the Institute is looking at all aspects of alien life. So we are not talking about little green men. What we are talking about is microbial life that can potentially be on other planets or moons within our solar system or outside of our solar system, and also potential intelligent life, which can also be potentially within our galaxy. So the SETI Institute actually has two different axes of study. One is with respect to biosignatures, as I was mentioning, microbial life, whether it's current or past, on planets like Mars or on the moon like Europa. And this October we have Europa Clipper that is going to launch to study that further, or Titan, right, which is the moon of Saturn. And the other axis is on technosignatures. So technosignatures mean finding signals or signs of technology anywhere in the universe, and particularly on exoplanets. So exoplanets being planets that orbit other suns than our own.
Right. Well, you mentioned Europa. What is Europa, and why is it important?
Right. So Europa, it's what's called an icy moon. So that means that with some past missions that were just doing flybys Jupiter and the moons of Jupiter, they observed that Europa is enveloped in an ice crust. But underneath this ice crust, there is a very vast ocean. And wherever you have water, there is a high probability of life. Now, the only way we can accurately determine whether there is life underneath the icy crust of Europa is by sending a probe, right? Sending a mission there to basically sample in situ and analyze the composition of the ocean on Europa. So Europa is one of the high probability candidates when it comes to finding these biosignatures within our solar system. So Europa is one, Io is another one, which is another moon of Jupiter, and Titan is another one. And there will be another mission called Dragonfly that will launch probably late in the 2030s and look for signals of life on Titan, which has oceans of methane.
Outstanding. So, any plans or analyses or studies in the works to look at planets outside of our solar system?
Yes, so that is the main purpose of the James Webb telescope. So the James Webb telescope is sampling through spectrometry the exoplanetary atmospheres on these exoplanets that orbit suns that are not our own sun, right?
Okay.
And through the composition of these atmospheres, scientists try to determine whether some of those chemicals or combinations of chemicals can be produced by biological processes, right? So you can infer from the composition of the atmosphere if there can be life on that planet. So going back to your question about my affiliation with the SETI Institute, it's actually then when my affiliation with the Institute came about, when I was part of this project with Frontier Development Lab, where we simulated the exoplanetary atmospheres based on metabolic networks. Okay. So finding metabolic networks on the surface of a planet, how will that processes, how will they change the composition of an atmosphere on that exoplanet, right? And we created lots of simulations and tried to understand what kind of combinations we can have at the microscale on the surface of the planet in these metabolic networks and the macro scale with respect to the planetary atmosphere.
So, as a computational scientist, what is actually your role in the search for life beyond Earth?
So I mostly look at data and analyzing data and at creating simulations. So again, we can have data with respect to the observation of the atmospheres, right? And we know what kind of compositions and chemicals are in those exoplanetary atmospheres. Okay. So we combine the data analysis with simulations. We also have data with respect to metabolic networks as we understand life on Earth, but trying to eliminate many of the biases or constraints that we currently have about life on Earth, because we are not looking just for life that is similar to life on Earth. We can look for life that can be quite different from life on Earth. Mm-hmm. So it's there where this idea of creating synthetic data from simulations where it comes in. So in the project that I was mentioning with metabolic networks, we actually took data from E. coli, which is has a well-known genome. And we modified that with zeros and ones, right? So we simulated that genome with zeros and ones, and then we created different types of E. coli that don't necessarily exist on Earth right now, and that could feed from or that exude other types of gases than the ones that we know that E. coli has on Earth, right?
Oh, really? So you were able to create this?
In the computer,
yes,
right?
In theory.
In theory, in the computer, right? And we, by creating these simulations, again, we were trying to understand which kinds of genomes or alterations in the genomes for E. coli could produce those kind of gases or combinations of gases. And we look particular greenhouse gases, which are more likely to be a biosignature for life on the surface. Okay. So again, which kind of combinations in the metabolic networks and the genome of E. coli could render those combinations that we can potentially observe with the James Webb telescope.
So another recent project of yours was an exploration of the future of Mars colonists through an agent-based modeling approach.
Mm-hmm. That's right. So agent-based modeling is a type of simulation. It's different than the simulation that I was mentioning for exoplanetary atmospheres. So in this case, with an agent-based model, we are able to model interactions between agents. And these agents can be people or can be animals. They can interact with an environment. Most of the times it's people, right? So in this particular project,
you were looking at people in this project.
In this project, we are looking at people. So this project came to me as So, a collaborator of mine, he basically saw this paper that was published by another author who used a mathematical model which was very similar to population dynamics models, and trying to figure out what is the minimum number of people that we can have on a planet so that we can sustain a colony on Mars in this case, right? So basically, how many people do you need to send to Mars so that you can have a sustainable colony there?
That's right. And I think he came out with, 22 people? Is that right?
No, that's my number. So he came up with a very large number, 150.
Okay.
And this collaborator of mine from Blue Marble Space Institute of Science, he came and he asked me, can I verify that number, right? And can we validate that? And at that point, my students and I, we created this simulation agent-based model where we looked at, okay, if we send people on Mars, assuming we have the technology, which currently, by the way, doesn't exist, right? So we're still working on that technology.
What do you mean? Elon Musk will invent it, right?
All right. So assuming we have that technology, which currently doesn't exist, okay?
Right.
And we can put the first man on Mars, which, again, it's still probably at least a couple of decades away from us. Let's say that, we can send some people to Mars, and how many of these do we need so that we can have a sustainable colony? In our model, our assumptions, I think, are a little bit more realistic than the pure mathematical model, in the sense that we assume that you can't really send 100 people at once, right? Any of these shuttles, they can have at maximum 4 astronauts. Mm-hmm. And assuming that you can send first 4 astronauts and then later maybe another 4 and so on, right? You create this colony, which, by the way, now we are referring to it as settlement. Okay. So there have been some debates in the field about terminology here between colony, habitat, settlement. So now we are more on the settlement side, right? Okay, so another assumption in our model is the interactions between people, which the other mathematical model did not have. And through the interactions of the people, these can have both positive and negative effects in terms of psychology, but also in terms of work and how they can live and work together in a habitat, which basically you are thinking of a very closed environment, right? It's not like you would be able to just roam around the planet given the inhospitable conditions. And we included in our model many factors with respect to how much air they would need, how much food, how much water, how much of that they can extract from the planet by breaking down the water that you can find on the ice shelves on Mars. And we accounted for that. We also accounted for resupply shuttles, because if we are to be realistic, it's not like you send a bunch of people on Mars and you just leave them there, right? And that's it. You cut off with Earth. Once you can send the first shuttle, you'd be able to send several others. And it's just like it happens now with the ISS, right? The International Space Station. They have resupply shuttles all the time. So we assume for that. And we came up in our simulations with a much lower number than the one that was advanced by that paper, 150. So in our paper, basically anything in terms of tens, right? So anything above 40, 50 people should be able to have a stable settlement on Mars. And the lowest number that we could come up in our simulation under very specific conditions was 22. So that's where that 22 number comes from. Those are based on, again, like very specific conditions with respect to how many disasters can be on the habitat, or how many disasters can be with the resupply shuttles. How long will it take? We also accounted for a technology factor, so we are assuming that in time technology will improve and that it will be able to send people and goods there in faster time than right now. The average is between 6 and 9 months. And we accounted for a very small improvement in technology too. But
you would need to have some mechanism, I presume, for people to grow their own food. Is that right?
Yes, that's right. And there are many scientists right now working on growing, for example, tomatoes out of soil that is very similar to the Martian soil. And what type of enrichment do you need to do for that specific soil so that you can grow food? And yeah, there are many people who are looking at, especially in botany, in the botany field, just like in the movie The Martian, right?
Just like in the Martian.
Yeah, they are looking though at tomatoes, not necessarily potatoes. So
Understood. So, at some point in time, you always should ask the question, why, right? What are the benefits to a future settlement on Mars? What do you imagine and what do you imagine it will look like?
Yeah, that is a very good question, because I've seen lots of articles in the media with respect to mining the moon or mining an asteroid or mining Mars, right? And there have been very few economic studies actually with respect to how much return on investment you can get from mining these really far away places.
Right. It depends on what's there.
It depends on what's there, but even let's say it's diamonds, right? Which many people say it's rare earth minerals or it's diamonds, and you'll bring them back to Earth. But once you bring them back to Earth and you flood the markets on Earth, the price will go down, right?
That's right.
So I don't know how much return on investment you can have with that. I think the bigger question with respect to both Mars and Moon is geopolitical one. So it makes more sense from the geopolitical advantage and from the scientific advantage than it actually does from an economic standpoint. Maybe later on, I don't know, decades from now, hundreds of years from now, yes, you can have a sustainable economy between Mars, Moon, and Earth, right? But it's something that it's probably not going to happen too soon.
Understood. So artificial intelligence is a major topic of discussion right now, and it plays a role in your work and in data science, obviously. Mm-hmm. How could AI play a role in a Mars settlement?
Mm-hmm. So that's a really good question. When it comes to studying phenomena that can potentially happen in the future, we don't have tons of data for that, right? Because it's something that's going to happen. It didn't happen in the past. In the absence of data, you can't really actually use AI. But another way through which we can look at this is either through synthetic data, so we can create data just like I was mentioning with the other project with the exoplanetary atmospheres. That's one way. Or another way, which we are doing right now, is to collect lots of case studies from proxy environments. So we advanced that project with the Mars settlement. We are actually now looking at the moon, and we are looking at how we can help the Artemis 4 and 5 program. So the Artemis 4 program will put space station around the moon. Artemis 5 will put the moon base on the south pole of the moon. So in order for us to be as accurate as possible so that we can actually help the program with that is by looking at the proxy case studies of human behavior in extreme environments. So we've taken as many case studies and literature that we could from research outposts in Antarctica, from the submarines, from oil rigs and other similar kinds of extreme environments, from the analog missions such as Mars analogs and Moon analogs that are on Earth, and obviously the International Space Station. And by amassing all that data, analyzing that, we are hoping to identify those nuggets of interesting human behavior or human psychology that will play a significant role in the success of these missions. At this point, we are looking at the moon, hopefully in the future at Mars too.
Oh, that's really cool. All right, so now we get to the moment of truth.
All right.
So I got a series of questions. We're gonna get a little fun here.
Sounds good.
If you don't mind.
Sure.
Okay. Question number 1. Do you believe that there is intelligent? Well, let me take the question back. Do you believe that there is life on other planets?
Yes, I believe the probability to find life on other planets, I do think it's quite high. If we are talking about all the planets at least in our galaxy, and let's not mention how many galaxies we know are out there.
Right.
Yeah.
Okay. So let me take that question to the next step. Yeah. Give me an idea. Give me your thoughts on intelligent life on other planets.
with respect to intelligent life, and there actually even the other life, are we talking about simultaneous life that exists right now, living, versus past versus future?
I'm talking about right now.
Right now, simultaneous with us.
Right
Okay.
now.
So for that, I actually have a low probability for that. We have the Drake equation,
Okay.
which actually is a good heuristic or indicator for us in how we can calculate these probabilities. And with the Drake equation, while we might have lots of planets within or exoplanets within the habitable zone, where life can develop and emerge, there is an entirely different question with respect to whether that life can evolve into intelligent life. That's one step. The next step would be, can that intelligent life evolve into a life that can create technology, right? Because maybe they won't, right?
Right.
But just with respect to intelligent life, we actually don't know that because we only have a sample of one, right?
I know. But let me throw out some numbers, and you tell me where I'm off.
All right.
We know that there is an estimated about 100 billion galaxies.
That's right. Yeah.
Okay. Each galaxy, each single galaxy has billions of stars, as does ours. And each of those stars has, in many sense, lots of planets on those individual stars, right? 100 billion galaxies, billions of stars, each with most likely multiple planets. And so if you use the Kepler data alone, it estimates 300 million habitable
In the
planets
habitable
with
zone, yes.
environments
Yep.
not too different from Earth.
That's right.
300 million. And
Yeah.
out of those 300 million planets, your estimate is very low
For
for
intelligent life.
intelligent life.
Yeah. So my
So
estimate
help me.
is
So
really
help me to understand why that, because the numbers tell me that by golly, there's got to be intelligent life.
So your numbers are correct in saying that the probability for life is high in generic. But now,
I'm
again,
not talking about amoebas and protozoans. I'm talking
You're right,
about
human-like, right?
Yes.
Yeah, intelligence, right? But again, evolutionary processes require millions and millions of years, right?
But we're a
the
young
question,
galaxy.
Yes, but the question is more about, are we early in the evolution of emergence of intelligent life versus are we late on that, right? If we are talking about galaxy times. So the question is whether they are simultaneous with us, right? And at the same level or similar level of intelligence with us. So that is actually a lower probability.
Yeah, I hear you. We think we're smarter than what we are. I'm telling you right now, my estimate is that it is a high probability of intelligent life in multiple planets.
But we also have the Fermi paradox, right? So if the probability of intelligent life is so high, then it means that we would have intelligent life at different levels of intelligence, and many of those would be more intelligent than us, right?
Yes, I
so
agree.
we should be able to detect those. So how come we haven't,
wait.
right?
Why would we be able to detect those? We're just now getting the capability to really see outside of our galaxy, right?
That's true. And also Jill Tarter, who is very famous in the technosignatures field, she said that basically we have only sampled just one glass, if we compare to an ocean, one glass of water when it comes to the whole universe.
I agree with that.
But again, when we are talking about different timelines here, so how long does it take for intelligence to emerge?
There could be others that are way ahead. There could be some that are behind,
That's right,
There could
yes.
be some in the middle.
Or extinct, yes.
Or extinct,
Yeah.
right? There could be some places where life was extinguished, intelligent life was
That's right.
extinguished millions of years ago,
That's right, yeah.
And so I just think there are too many possibilities. And actually, life occurs so easily, right? It's not hard for, I'm not talking about intelligent life. I'm talking about just life in general. It occurs so easily here, even in places where we think of are inhospitable.
Right.
You wind up finding life in places where you never thought, right? In volcanoes and in really cold subsea areas. Right?
Yeah, in hydrothermal vents, that's right. In sulfuric acid type of environments, that's right.
So you find this life, you would never have thought that life could exist in these entities, but we are finding it. So my philosophy is you got to hold out the possibility for significant life. Now, but there's one other thing. You study this whole concept of unidentified anomalous phenomena, right?
Well, I studied it while I was part of the independent study at NASA, but I'm not studying that right now.
Okay, so let's pull back from that. Let's ask that. There are thousands of unexplained cases of phenomena, some of which, when you look at it, you say, oh, that looks strange, right? I got a friend who's a pilot.
Yep.
Who was a pilot in the Navy. And he's like, look, I'm telling you, what I saw wasn't human, but it was real.
Yeah.
You get what I'm saying?
Yeah, absolutely.
And when somebody with a trained military eye tells me that, and I know him, then I'm like, okay.
Yeah.
Okay, so we got hundreds of cases of this stuff.
Sure. We have lots of reports from pilots, not just in the military, actually, some commercial pilots as well.
But I trust a military pilot differently.
It's not that we don't trust these testimonies. We trust all testimonies, and we know that people are convinced of what they see. But also our brains are highly trained to identify patterns where patterns are not, right? Like finding Jesus in a loaf of bread, right? Or finding the shape of a dog in the clouds, and so many others, right? Because that's how we are wired biologically.
I know, but these cases are beyond that, right? When a guy's flying an aircraft and he's looking out of his window, and a few hundred meters away from him, he sees another craft.
Sure.
And that craft takes off with a speed by which he can't even, he's already at, Mach 1.5 or so. This thing takes off and leaves him standing still. He's like, okay, that's something that is not human.
What I trust more than any human, no matter how well trained they are, including astronauts, is sensors and sensor data. And we can make sense only what we observe with respect to velocity, heat patterns in these phenomena. So unless we can observe these and we can compare them with ground truth. So it's not that they didn't see something, but it's what did they see, right? So that is the question.
Right. No,
so that's a huge leap from seeing something that you don't know what it is and it's unusual and you cannot explain it versus having a leap that is alien life, right? There is no connection there.
But we have to understand that if you are to see something like that here, they have discovered physics that we may not have discovered yet.
Sure.
Right?
Yes.
Until Einstein's theories of relativity and others, we had an understanding of the world that people kind of accepted. And then here comes Einstein with these theories that turn it on its head.
Sure.
That it took 20, 30, 40, 50 years to validate some of these theories, but almost everything that Einstein has outlined, actually everything, has actually been validated and been verified. But many itinerant scientists, when he put his theories forward, suggested they were not true because of exactly what you're saying, because there were no physical phenomena to validate it, right? And it was only after the physical phenomena began to become, people, ran studies to show, actually, time does dilate. We can show that it dilates, right?
I mean, for us as scientists, we can only, and not just scientists, we can only do what we can do within the science and the history that we are at right now, right? And there will be probably new discoveries in physics that will be very interesting. And then my question to you right back is that, okay, if there is physics that we still don't know, then why can't we assume that these UAPs are a physical phenomenon, right, of a physics that we don't know yet?
That they may encompass some physics. So think about it this way. If you had to travel from another galaxy and get to this one, right, it would require some physics that we just don't have, right?
That's right, because with the threshold of the light speed right now, it's impossible to actually travel between galaxies. And let's not forget that the universe is expanding, right? And actually the space between galaxies is only increasing.
That's right.
And up to a point that I don't know how many billions of years, our skies will be completely dark because we won't be even able to observe any galaxy. So imagine if you have a life form in those times, they won't even be able to even conceptualize or comprehend that there might be other life forms in other galaxies because they wouldn't know other galaxies exist.
But over that time, their level of thinking and thought will actually progress. And
if we assume continuous evolution in civilizations, but given the past of our civilizations, we don't know if a civilization is going to survive that long, right?
You are bringing up really deep, but this is great.
Yeah.
This is the kind, and this is why I love these kind of conversations, because this is the kind of thing that our young people, our students, even our faculty and staff, it's the kind of thing that people should be talking about, be. These discussions, because they actually can lead to broader, more substantive discoveries, right? I mean, the reality is, if you were to be able to travel at those speeds and those distances, you probably wouldn't be using combustion, right? Because you would need a different kind of fuel.
That's right.
Which means that you'd probably have a very different heat signature. So if you see something that moves at a very, very rapid speed and takes off, and you say, well, look, the sensors didn't show anything with a heat signature capable of those speeds.
Yeah.
Maybe the answer to that question is,
even
the physics
right
associated
now,
with that didn't leave a heat signature because you're probably not combusting, right?
That's right.
And so
even right now, if I may say, JPL is working on an ion propulsion engine for Mars, right? So we won't have that kind of heat signature for if we really want to go into deep space and do human exploration into deep space.
Ion combustion. Are they using the technology that was gathered from the aliens at Roswell?
Absolutely. Of course.
Anyway, to me, these are the kinds of conversations that we should have.
Yeah. So, no, absolutely. I mean, there is actually a good friend of mine. He is looking at the timeline of civilizations and whether 1 million year long civilizations can exist, right? And we can actually do that right here at George Mason with computer simulations and grow artificial civilizations in computers and see what are the thresholds under which those can self-destruct.
This is good because at some point in time, as our models, as the fidelity of our models become better and better, and we're able to process more and more data with artificial intelligence, I think the bots are going to come back and tell us this is about how much time you have if you continue living like this. Right?
I mean, there are so many variables for any civilization.
But we have so many. I'm saying before parts of our planet literally become inhabitable, right? I mean, you're down in Florida, you get hit with a storm, then you get hit with another one. What happens if you get hit with 4 or 5 right after that, right? At some point in time, people say, look, I'm not going to live there because I'm basically, my home is destroyed every year. So these aren't far-fetched notions. It's definitely not a far-fetched notion to somebody who lives in that part of Florida right now. The debris from one hurricane wasn't even removed before the next hurricane came in. And so and we're moving to a reality where you can have 1, 2, 3, 4, 5 of these in a row, right? And so this is a real occurrence that we have to think is possible. And we have tools now
Yeah, that's right.
That can help us discern that.
That's why we are looking at extreme environments and how can humans survive in extreme environments that are not necessarily in space, but this will definitely help us get into space, perhaps, so that we can live in space, and also help us understand how we can survive the extreme environments right here on Earth. And going back to what you were saying, exactly these kinds of questions can lead not just with respect to are there aliens, but can help us understand many other things with respect to what do we need to have long-living civilizations, what is intelligence, what is actually life, because we don't have an accurate definition of life right now. They can help us perhaps identify the origins of life right here on Earth. So all these questions are actually related to this broad field of astrobiology. So when we ask questions with respect to are we alone in the universe, we are touching upon so many other things, in geology, in chemistry, in social sciences, in computational sciences, in artificial intelligence, and so on.
I love it.
Yeah.
Let me wrap up here, but because you're not only an accomplished professor here at George Mason, you're also an alum.
Yes,
right?
I am. Yes.
And you earned your PhD in computational science in 2012.
Yeah.
And so now you entered George Mason's computational science doctoral program while you were working on another doctorate, a PhD from the Academy of Economic Studies in Romania.
Yeah,
right?
That's right.
And you completed your first PhD while you were taking classes at George Mason. But what inspired you to do a second doctorate? Because that was fascinating too.
So my PhD in Romania is actually in economics, right? But at the time, I was really fascinated by the idea of complex systems and what are complex systems and system dynamics and these kinds of things. My PhD thesis was with respect to complex systems in economics. But I wanted to do more, and I've always wanted to do research and to do science. So that's why I applied here. I came here, and it just happened actually to have the overlap between being accepted at George Mason University with a fellowship and trying to finish up my other doctorate there. And I wanted to do more and to expand more beyond economics into this idea of complex systems, because as you can see, I really like interdisciplinarity, and I like to...
That is clear.
And that I like to dabble into several sciences, into many sciences. And complex systems was one way. Astrobiology is another way through which I can find out more about really important and big problems, how we can ask questions, how we can apply science regardless of the science, and apply many methods, right? So that's what I actually like, to be able to dabble into methods between statistics and mathematics all the way to computational methods that can be anything between simulations, deep learning, natural language processing, and so on. So I think as scientists, we kind of have to have, a big toolbox and really good critical thinking. It's something that the economics field actually gave me, how to think critically and very rationally about problems. And then just interacting with different scientists in different fields has been really, really beautiful.
That is so cool. How do you see the work that you've done in economics, the learnings that you had, how does that influence your work in astrobiology?
Oh, that's a good question. So once is through critical thinking. So as we had this debate about probabilities, low versus high, I really don't take anything at face value, right? So I try to do my own research. So that actually comes from economics. Another thing that comes from economics is counterintuitive thinking. We are wired towards intuition and taking leaps in our brain, causal leaps, which are not necessarily causal, right? So correlation is not causation. So that's something that also came with me from economics. And then another thing that actually came with me from economics into astrobiology is something that you asked me a little bit in the beginning with respect to economic and social effects. And it's something I'm tangentially interested in what kind of social effects we can have when we have big discoveries. If we really have an announcement, right? We found life. How will that have an effect into society, into economics? I'm not studying that, but I am in touch with people who are studying that. I am a part of the Post Detection Hub, which is a hub hosted by St. Andrews University. And I'm also in the Post Detection Committee at the International Astronomical Society, so that we can understand better what kind of protocols on the policy side we might need so that we can actually come together as a planet with multiple countries, with different understandings of space and alien life, right? And how we could mitigate any of the negative effects we might see in society when announcements of big discoveries are made.
So you were also the first woman to earn a doctorate in computational social science from George Mason University.
That's right. I was the 5th graduate and the first woman right here. Yeah.
Outstanding. So do you view yourself as a trailblazer in STEM?
No, not really. I mean, I see myself as someone who is really passionate about my work as a scientist, right? Mm-hmm. And if my work is meaningful and impactful, I'm really happy about that. If students can learn from me, especially my students, and if I can work closely with my students and my collaborators in these cool teams, that's really nice and important for me. If trailblazing is an emergent phenomenon, speaking about complex systems, right, is something that emerges out of this, it's fine with me. But yeah, it's not something that I really want to be a trailblazer. No.
Well, that's most people who become trailblazers are not necessarily seeking to become that. They just doing their work, right?
Yeah.
What do you hope other women in STEM can learn from your success?
They can do anything they want to do if they really pursue what they like, their passions, but also not to pay too much attention to trivial things, to follow their own path. It might be hard sometimes, but find good mentors and find good teams to work in.
Well, we're going to have to leave it there. Anamaria Berea, thank you for joining me to explore and explain some of the great unknowns of outer space.
Thank you.
I'm George Mason, President Gregory Washington. Thanks for listening, and tune in next time for more conversations that show why we are all together different.
If you like what you heard on this podcast, go to podcast.gmu.edu for more of Gregory Washington's conversations with the thought leaders, experts, and educators who take on the grand challenges facing our students, graduates, and higher education. That's podcast.gmu.edu.